All right, we left off in part 2 talking about the valence shell, or that outermost electron shell, and how it is what physically interacts with the world around it. Okay? This inner shell doesn't make contact with the outer world because it is surrounded by the second shell. Okay? So it's that outermost shell, or what we can call the valence shell, and those electrons in that shell are called valence electrons. Those are what actually interact with the world around that atom. Consequently, when you have an element that has a full valence shell, it becomes chemically inert, meaning that it cannot participate in any chemical reactions. Neon is an example of that. It has 2 in its first shell. Those electrons never see the world around it. The electrons in the outer shell, which there are 8, makes for a full second shell. It has no way of interacting with the world around it. Now is a good time to point out the concept that chemical reactions largely come down to sharing or donating or accepting electrons from another element. Okay? So this element cannot, if it were to donate something, it would be less than 8. It would be less happy. Okay? If it were to gain 1, it would have to put it in the next shell out, and then that shell would be almost empty. It doesn't want to do either of those two things, so it doesn't do either of those two things. Now let's go back and look at this periodic table again. Here we have lithium. It has 1 electron in its outer shell. It needs to have 8 in order to be happy or fulfilled, whatever you want to call it. Okay? That has a lot of ways for lithium to interact with the world around it. Okay? Carbon has 4, so it could interact in 4 different ways, or it needs to gain or lose or share 4 more electrons to have a full shell. So it can do a multitude of different things. Fluorine has 7. It only needs to gain 1 more to have a full outer shell. Okay? Let's look at sodium. Sodium has 1 in its outer shell. It is very similar to lithium, which has 1 in its outer shell. Okay? Let's take a look over here at fluorine and chlorine. Fluorine has 7 in its outer shell. Chlorine has 7 in its outer shell. Consequently, fluorine and chlorine behave very similarly in chemical reactions. Lithium and sodium behave very similarly in chemical reactions. Okay? And in this case here, the easiest thing for lithium and sodium to do would be to somehow lose that outermost electron. Because if it just lost that 1, then the next shell down is full. Let's take a look at fluorine and chlorine. It just has to gain 1. Okay? Carbon is a little bit more different. Okay? It has to gain 4 or lose 4. Okay? So consequently, it's going to behave very differently than lithium and very differently than fluorine. Silicon also has 4, so it's going to behave very similar to carbon. Okay? This is actually how we have this table set up and explains the rows. Okay? All of the elements in this row have 1 in its outermost shell. All the ones in this row have 2 in the outermost shell. All the ones in this have 3 in the outermost shell. 4, 5, 6, 7, and over here we have 8. Okay? This also explains why helium is all the way over here. Because remember, helium only has 2, so you might think, well, it would fit there, but it only has 1 electron shell. Consequently, it is full when it has 2. Helium, like neon and like argon, are completely inert. Okay? Argon is actually used in welding because it is completely inert. It can fill the space around where the welding is taking place, which involves very large amounts of electricity flowing, so much so that it melts the metal. Okay, melted metal is very reactive. By flooding it with argon, we help prevent that metal from reacting with things such as oxygen, which are naturally in the environment. Okay? So all of these are inert, and that is why helium is placed all the way over here, even though it only has 2. Okay? So let's go back here and think about how we're representing this. Notice how we have 2 electrons that are kind of paired here, 2 paired here, 2 paired here, 2 paired here, and 2 paired here. Why do we represent it this way? Okay? And the reason why we represent it this way is these electrons are occupying space in a slightly more complicated way than we've initially described it. We've kind of been describing these electron shells as being spherical places, okay, or spheres. And that is true for some of them, but not all of them, okay? So let's take a look at this first orbital, this 1s orbital, okay? It is a spherical shape. The 2s orbital is a spherical shape. Each one of these orbitals can actually only carry 2 electrons. Okay? But wait a minute. Didn't we say that the second energy shell can hold a total of 8? Well, that's true, but only 2 in this s orbital. We fit all of the other ones in a slightly different space. Okay? So we're kind of imagining here the electrons orbiting this nucleus. This is one way of orbiting. There's another way of orbiting, okay? And that is using this shape here, this kind of double barbell infinity shape type of thing, okay? Here, the electrons can spend time out here, and it can spend time out here, and it only transiently passes through this 2s orbital, which is represented here in the background, or this 1s orbital, which would be inside of this 2s orbital. Okay? So we will refer to this as a p orbital. Okay? Now, I'm going to go ahead and take away this background 2s orbital to get it out of our way. And if we can do this, then you could also stand to argue that we could do this. Okay? And so this becomes another spot where we can put 2 more electrons. So 2 can fit here, 2 can fit here, 2 can fit in here, 2 can fit in here. Okay? Remember, this is a 3-dimensional space, so we could also come out of the screen and back behind the screen, okay, which we'll represent as this orbital. Again, we can fit 2 here. So here we can fit 2. So we have 2 in the 1s orbital, or in the first shell. In the second shell, we have an s orbital, and we have 3 p orbitals. So consequently, we can fit 2, 4, 6, 8. Okay? We oftentimes represent these p orbitals along the XYZ axis of a coordinate system. Okay, so sometimes we can refer to this as the 2p sub x orbital or 2p sub y orbital. Okay, so let's take a look at all of these shells superimposed on top of each other. You can see in here we have the 1s on the inside. Surrounding it is the 2s, and then fluttering in and out, but mostly spending its time out here or out here, is the first p orbital. And then we have the second p orbital in here, and the third p orbital. Okay, so when we relate this orbital idea to this representation, we can say we can fit 2 in this first s, we can fit 2 in the second s, and then we can fit 2 into the p orbital on the x-axis, 2 in the p orbital on the y-axis, and 2 in the p orbital on the z-axis. Now, you might be asking yourself, well, why 2? Well, that gets slightly more complicated, and again, I'm going to say it's above our pay grade. So if you want to talk about it, we can talk about it privately, or you can wait for chemistry. The short answer is these 2 electrons are actually slightly different, but in a way that doesn't change them being electrons, okay? And it allows them to share space together and become paired. For a longer answer, take chemistry. So, this concept 2.2, an electron's properties depend on the structure of its atoms. So we figured out that the structure of an atom is we have a nucleus that has protons, which are positive, and neutrons, which are neutral. They're together in this nucleus. They're larger and have mass. Then we have these electrons, which almost have no mass. They have ever so slightly some, but they are negatively charged, and so are attracted to these positive protons, and they orbit around in these shells. These shells are defined space and have defined potential energy levels. Those electrons can shoot up 1 or 2 energy levels, and then it can release that energy and drop back down. Those electrons can be in this shell, in this shell, in this shell, but it can't be below the shell or in between the shells. It has to be at one of these energy levels. Okay? We discussed how there is an outer electron shell. That outer electron shell, if it is completely filled, makes an element inert. Okay? That outer shell is called the valence shell, and it is what actually or physically interacts with the outside world. So we can see here that as we look down, hydrogen behaves very similar to lithium and very similar to sodium because they all have 3 or just a single electron in its outer shell. Carbon and silicon behave very similarly because they have 4 in their outer shell. Fluorine and chlorine, very similar because they have 7 in their outer shell. And this filling of these outer shells, either by borrowing, taking, donating, or sharing electrons, is what gives each individual element its chemical characteristic. We represent these as paired electrons, and there's 2 in the shell and 8 in shells 2 and 3 because these are broken up in space. We have a 1s orbital, which is spherical in nature. We have a 2s orbital, which surrounds the 1s orbital, but is again spherical in nature. Then we have 3 p orbitals along all 3 axes of 3-dimensional space, and they spend time out here. Very rarely do they pass through the middle. Okay? Maybe out here, or over here, over here, over here. Each one of these can hold 2. So 2 here, this is filled. 2 here, 2 here, 2 here, 2 here. We have a total of 8 that can fill this second shell. Okay? And how these shells overlap each other defines its chemical reality. Notice how that energy shell 1 is completely hidden by the combination of all the various shell 2 orbitals. Okay? And so consequently, it's only the outer shell or the valence shell that makes a difference. All right? And that is concept 2.2. I know this was a long one. There was a lot of meaty material to get into there. You might want to rewatch these a few times to get the hang of it.